In this video, we're going to talk about some of the forces that appear most often in the problems that we're going to be solving. Let's start with weight. And in talking about that, we're also going to talk about mass. So mass and weight, you can think of mass as the amount of stuff that a body has, and weight, which we denote by W, this is a force and is due to the pull of gravity from the earth on the object. So they are not the same thing, right? So so for the weight we use the vector to represent the quantity. For the mass we just need one number, right? So a mass is just the amount of stuff. So in the international units, right? So kilograms is the unit for mass and newtons is the unit for weight. In the US system, then slug, that's the unit for mass, and pound is the unit for weight. So the weight, the force of gravity on an object, is the mass times g. G is the acceleration of gravity, which is 9.8 meters per second square. So let's look at the units again. 1 pound is 4.45 newtons. So 1 newton is about a quarter of a pound. And mass, right? So the mass is basically 1 kilogram is equivalent to a force of 2.2 pounds in a gravitational field of 9.8 meters. But remember, pounds are units of force and kilograms are units of mass. So there is a concept that appears a lot. It's that of apparent weight, and that is the force of gravity when things are falling or going up, right? So the weight of an object due to the force of gravity. Now, the sensation that you have for weight is due to contact forces on your feet supporting you. So that sensation is what we call apparent weight. So let's look at an example here. So imagine that you're on an elevator and the elevator is going up and there is an acceleration, right? So what is your free body diagram? Well, you have the real weight, that's the pull from gravity from Earth, and the normal force, right? So now you have the normal force minus the weight, that's equal to ma, right? So the normal force is greater than the weight. So you can think of this normal force as the apparent weight. If you put a scale here, right, to measure your weight, it's not, let's say you weigh 150 pounds and just put a scale there, then the scale is going to read maybe 170 pounds, right? Because you're going up and then the normal force on the normal force is going to be greater than the weight, and this normal force is basically the apparent weight. Let's talk about normal forces a little more. Normal forces are the forces that a surface exerts on an object, right? It's always normal to the surface, right? So if the surface is like this, normal force points like that. If it is inclined, normal force points like that. If the surface, this is the surface here, this is the surface. If it is vertical, then the normal force points like that. If it is a ceiling, the normal force points down. So the normal force is perpendicular to the surface. Always remember that, and pushes back. So here, for instance, let's see what happens. We have a book on a table, and then if there is no hand, then you get normal force and weight. They cancel each other. Now, as soon as you start pushing down, the normal force increases, right? So then you're going to have the force from the hand, the weight, and these two have to cancel the normal force. So the normal force is proportional. So it's a force that points up in this case, and it's a force that has to cancel both the weight and the force from the hand, so the object stays on the table. If you have a surface that is sort of an inclined plane like this, then the normal force is perpendicular. So this is a typical free body diagram. So the weight has two components. This here typically goes with the sine of these angles. So that's a nice thing to remember. You don't have to remember that, but it's good. This angle is the same angle here, right? These two angles are the same. If you draw a triangle here, this is theta, right? So this is theta too, right? So these two angles are the same. This component here is the x component of the weight, W sine theta. That's what causes the A sine theta acceleration that we saw in the kinematic last week. And this component here, that's the one that cancels the normal. That's W sine cosine theta, and that one cancels the normal. Never do this. If you have an inclined plane, right, here, the normal is not going to push up, it's going to push in this direction. Remember that. And the weight is going to push down. It's never going to push along this direction. Let's talk about friction now. Friction is the force that opposes motion, and there are two types of friction: statics. There are actually three types of friction: static friction, dynamic frictions, and kinetic frictions, and rolling friction. Let's start with static friction. If you're pushing this box here, this crate, so if you start pushing, it's not going to move. There is a friction force that opposes any motion and keeps it at rest. That is the static friction. If you keep increasing that force, eventually it's going to move. You reach the maximum static friction. So the friction force that opposes the motion and keeps this crate at rest, that is a static friction. This is a free body diagram for this crate. You have your push and your friction, they cancel each other, and then you have the normal and the weight. So as you keep pushing, right, as you increase your push, the static friction increases. Eventually, the static friction is going to be max, and then you're going to be able to move the crate. That value of maximum static friction is proportional to the normal. We find that experimentally. There is a constant here, we call that the coefficient of static friction, right? And so the static friction is the coefficient of static friction times the normal. This is the equation that you more often are going to use in the equations to solve problems. So the static friction opposes the motion. Static friction increases to oppose the motion, and when it reaches the maximum value, then you start moving the object, and that maximum value is the coefficient of static friction times the normal. Kinetic friction, on the other hand, is the friction that is there once the object is moving. So you have a velocity here, right? So the object is moving. You have a push and the kinetic friction, and this push has to be greater than, well, this push doesn't have to be greater, it has to be equal to the kinetic friction for the object to keep moving at a constant speed. It could also be higher, and the object is going to be accelerated. The kinetic friction is always equal to the kinetic friction coefficient times the normal. Don't confuse this with the static friction coefficient. These are two different numbers. Okay, so this happens when there is kinetic friction. This happens only when there is maximum static friction. Rolling friction is the friction on wheels, and is also written as a coefficient times the normal. So here are some values for friction coefficients: rubber on concrete, static friction of 1, kinetic friction of 0.8, rolling friction of 0.02. You have steel on steel, steel on steel with some lubrication, see how much it goes down. Wood on wood, wood on snow, and ice on ice. This is very small. So see, that's why you can do skiing. So static friction. So this is the equation you're going to use only when you reach the maximum static friction. Kinetic friction, this is the equation you're going to use. And rolling friction, this is the equation you're going to use. A drag is a force that is due to the air, is always proportional to the velocity and opposite direction. It's very complex, so we're not going to go into the details. There is a nice write-up in your textbook where it explains Reynolds number. I advise you to read that to understand a little better how drag works. Okay, so now let's look at interacting objects and Newton's third law. So here we have two objects and we have the hand applying a force. So we have two objects, so we need two free body diagrams. We need one for B and one for A. So B has a force from A on B, right? And that's it. That's the free body diagram for B. What is the free body diagram for A? Well, A would have the force from the hand and a force from B on A. Notice that these two are an action-reaction pair. They are equal and opposite. They are equal forces with equal magnitude and opposite direction. So let's look at the free body diagram for those two. So you have free body diagram for B, free body diagram for A. This is force from A on B, and this is force from B on A, and those two are equal and opposite, and this is the force from the hand. So when you solve problems of interacting objects, you are going to have to use two or more free body diagrams, one for each object. So now let's look at our final point here, ropes. Ropes are going to be in this class massless strings. We don't consider them to have mass. So the approximation we're doing is that the mass of the rope is very small compared to the object. So then we can neglect the mass. And then there is a tension that is passed completely from the hand to the object. So the force here is the same force here, and it's the tension. The final thing that we are going to look at is pulleys. And pulleys are objects that basically, when used with ropes, they change the direction of the tension. So here you have this nice example of two objects. So you have a free body diagram for this and a free body diagram for here. And the key to these problems is that the tension here is the same as the tension here.